Welcome to From Zero to Knowledge by House of ZK. Today we're going to be talking a little bit more about zero knowledge proofs. My name is Ashley and I'm joined today by Vanishree. In our last video, we talked about the 3-graph coloring and you explained how a zero knowledge proof could work. So is that still how they work today?
A lot has evolved since then. This is one of the first protocols when zero knowledge proofs were invented back many decades ago, and the evolution has happened in many dimensions. So it'll be good to understand what those dimensions are and how, in what ways the evolution has happened. So we know that there is a prover and there is a verifier, right? I've also written a related dimension of proof generation and verification. This is the process of running these algorithms. So this is one set, this is another set. And then there also is a setup. This is a third component.
Is this a trusted setup ceremony that we hear about?
It's, yes. So setup can be run either through a trusted setup ceremony for some protocols, and some other protocols don't need a trusted ceremony to do this. It's not trusted. So yes, you're right that this is that setup that we are talking about. And then there is another dimension of developer experience where evolution has happened. So let's go through each of these dimensions and see how the evolution has happened, in what ways the evolution has happened over the past few decades. For a prover, so to recall, there is a prover and there is a verifier, right? In the example that we saw, there was interaction between the prover and verifier. And this can become not ideal in many situations where there is no one verifier, but there can be anyone wants to be a verifier.
Okay, so you would try to prove something and anyone should be able to tell whether that was true. Okay, exactly.
So the way it works is that I will generate a certificate of sorts. It's a proof and publish it. Anyone who looks at it can run the verifier on this certificate and get convinced. So there is no interaction. There is no requirement for a verifier to be present when the proof is generated. So that is one dimension where one way where evolution has happened. And the version of those zero knowledge proof protocols where there is no interaction with a few other properties, they are called ZK SNARTs. S here stands for succinct. N here stands for non-interactive. Okay. ARK stands for argument of knowledge. And there is no need to get into what argument of knowledge really means. It is a little more technical than required. We now know why it's called non-interactive, because there is no interaction. It's non-interactive, succinct, because the proof is small. ZK sparks. And another way the evolution has happened is faster proving. Low memory requirements for proving, because proving can tend to be very resource exacting. And these are the ways where research has happened to make things better. Faster proving, lower memory requirements, and some components of proof generation have this ability where you could parallelize that a lot, and you could take advantage of that by having this hardware, specialized hardware optimized implementations, where, for example, GPU accelerated implementations of proof generation. That is one way where evolution has happened. The advantage of parallelism in proving is that you can shard the computation into multiple pieces and give it to multiple little devices with lower memory requirements, for example. And the other way, the final way where evolution has happened is through this concept called recursion, where you can actually prove another proof. where you have a proof and then you prove that this proof is correct, and get a proof, then you prove that this proof is correct.
Proof inception.
Proof inception. It's fine. And this is useful. So a great example is one of these projects that I worked on. It's called the Mina protocol. It's one of these early embracers of ZK, where the recursion was very important, where the idea was that you have one single proof that stands in for the correctness of the entire history of blockchain. There's one single proof to verify that the entire history, be years of history of a blockchain, to verify that instead of downloading a huge, hundreds of gigabytes of data and slowly verifying it with huge memory requirements. Don't do any of that. Use the power of recursion, where at any given point in time, you have a proof that stands in for the correctness of the history. You add more transactions to the blockchain. You update the proof, and that proof says that the previous proof was correct and the new transactions are correct. So at any given point in time, there is this one single proof, which is succinct, that stands in for the correctness of the entirety of the blockchain. And he was one of the early users of recursion property. And it's an extremely powerful property and is quite used today. So this is one dimension where a lot of advancements have happened. Any questions so far?
So basically, now you don't have to wait as long for me to do all the guessing. And I don't have to remember which guessing I chose before. So we've reduced the amount of memory that we need. It goes a lot more quickly. And we can use a proof within a proof to make sure that the data is accurate. Perfect. Great. Yes.
And now you see, we did all of this. Why? Because proof generation tends to require a lot of resources in terms of compute time and memory. And imagine a project that is trying to embrace ZK, and it is trying to think what is the infrastructure on which it can generate proofs. So there's a protocol, there are users need to generate proofs, or the protocol needs to generate proofs. Validators might need to generate proofs. So where will they generate proofs? Do they need to bring their own hardware? Do they need to spin up instances on Google Cloud or something? Because it tends to be expensive. What is a good solution? Because there are some interesting properties of ZK that can be used in optimizing proof generation. And can we build an infrastructure that is optimized for proof generation, that can do this proof generation in a cheap, performant, and reliable manner, and can adhere to any instance in the world, any proof system, any chain, any virtual machine, any situation in the world where they don't have to worry about proof generation at all? Where do I generate the proof? You don't have to worry. Can we remove that headache away from people? The market, it gives out a proof. All the headache is in the background. You don't have to worry about it. And this is exactly what Fermah that we are building. This is exactly what we are building at Fermah.
Very cool. So instead of me having to do all of the work, I can shut one proof bucket.
Okay, exactly. So this is another dimension where advancements have happened. And regarding the verifier, right, there was a prover and there was a verifier. So typically in Web3, verification happens on-chain. Proof generation happens off-chain. So there isn't a huge much advancements haven't happened here because it's not that much necessary. We have this protocol called GROT16 or Flonk. There are these special zero-knowledge proof protocols where the verifier is anyway very, 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 very lean. It is a typical protocol that is used for as far as, so you do a little bit of recursion. There is a final proof, and that is that GROT16 proof or Flonk proof, so that the verifier is really small. So that's the verifier on-chain verification there. And now the question is, even when the verifier is really small, when you do a computation on chain, it can tend to become expensive. For example, if you put verification on Ethereum, if the activity is very high, the cost of running that computation can be very high. And every time when there is something like this where it can become more expensive, there is a need to figure out how we can build an infrastructure where this doesn't become that expensive. And that is why there are these two directions of advancement in as far as verification is concerned. One is there are these new settlement layers. Ethereum is Ethereum or Solana. Solana is also embracing ZK. Bitcoin is also embracing VK. They tend to be the settlement layers where when these protocols say that verification is done is when you believe that verification is done. So they are used as the settlement layers. But they can become expensive. So there are these other settlement layers like ZK Verify, Aligned, Layer Edge, etc., where they're building their own layer, their own protocol where you can settle proofs, meaning that you can use those protocols to verify your proofs.
So without having to wait for any network latency on, like, so you're using Ethereum or pay for higher gas speeds.
Exactly. Gotcha. Exactly. So this is one direction. The other direction where you can actually reduce the cost of a proof verification is that instead of, so let's say you have a protocol where your people are generating proofs, and you don't verify every single proof on chain. Instead, what you do is you put them all together and create this, you remember recursion? You put them all together and generate one single proof. Let's say for every 10 proofs, you generate one proof, and instead of, you're reducing it to 1/10.
Gotcha.
You're reducing the verification cost to 1/10.
So I just verify the one proof, and it says that all of these others are also correct.
Exactly.
Gotcha. Right.
And this is not a recursion, but it is an aggregation. Recursion is really, really powerful. You can keep going in recursion. Aggregation is that you have a bunch of proofs. You just arrive at one single proof for a bunch of proofs. So there are aggregation protocols like Libra, Aligned, and I think Electron Protocol also we're working on this. There are these aggregation protocols which are working on this technology, and there's a huge amount of advancements here too. So we looked at a bunch of advancements for the prover dimension, for the verifier dimension, and for the setup dimension. Like you correctly guessed that this is related to trusted setup ceremonies. There are a few advancements here. Before we look at those advancements, let's recall something that we just discussed. There are two kinds of protocols, zero-knowledge proof protocols. One kind is where you need a trusted setup, and the other one where you don't need a trusted setup. When you don't need a trusted setup is when they're called transparent. There is nothing trusted. There is nothing up anybody's. So there is no secret there.
Okay.
So it's called transparent. That's why they are called transparent. And instead of being called ZK stars, there are a few other definitions of ZK stars, but this is a definition of the ZK star, where T stands for transparent. Now, let's look at the kind where a trusted setup is required. When a trusted setup is required, you can either assign one person that you really trust, that all of us really trust, and that person will run a trusted setup. And the goal is that they shouldn't do it maliciously, and they have a little secret that nobody should know. Right? So they're trusted with that little secret and also with the correct running of that computation. But we don't have such a person in Web3 because it's all distributed. Nobody trusts anybody. Which is why we run a trusted setup ceremony where multiple people around the world come together and run a protocol where no one single person knows the secret, but we all contribute our contributions to the secret, and we get that step. That it's a parameter, set of parameters called parameter, right? We all come together, run this so-called trusted setup ceremony, and we generate this setup. So that's trusted setup ceremony. And there are two ways where advancements have happened. One way is that it's ideal if you don't do, it's ideal if you can run one trusted setup ceremony for various competitions. Where we did one for graph tree coloring. Maybe there is another competition. Can we run one single ceremony because it's operationally expensive to run a trusted setup ceremony around the world? And a universal trusted setup was an invention that helped make this possible, where you have one setup ceremony that can actually compute a lot of computations. And the second one is that it is updatable. Let's say 1,000,000 people got together and ran this trusted setup ceremony. And I'm just a cynical person, let's say, and I don't trust anybody. And I just want to make sure that this setup is nice for me to use and generate proofs with. It's updatable. This setup ceremony, the parameter, is updatable. I can contribute my own contribution to this setup and use another version. So it now is a newer version of the setup parameter because I've contributed my own version and I can use it. And the idea is that there are these protocols, the trust setup ceremony protocols, where you just need one person to be honest.
I see. Okay.
All the other 1,000,000 people can be bad. So universal and updatable.
So you've decentralized the trust aspect, right? And then with the updatable piece, it's like you've sort of created a template that anyone can modify for their own use.
Right.
Okay.
Conviction that the setup is perfect. There is no malicious activity happening. There is nothing malicious about the setup parameter. You can come to that conviction through the property of updatability.
Gotcha. Okay. So how has the developer experience changed?
Right. So recall that our goal is we start with a computation and we want the ability to prove that computation. Computation can be expressed in many ways, but there is a certain way that zero-knowledge proofs understand. There is one language where math language where zero-knowledge proofs understand. So we need a way to go from how developers think and write to the way proof systems understand. And part of this is called arithmetization, the process of going from computation to the language that proof systems understand. And there are two ways of going this route. One way is through custom circuits, and the other way is through CKDNs. So what's a custom circuit? It is this representation of computation as a set of constraints, and that's called a circuit. It's just how it is called. It's called a circuit. And you can build those custom circuits, custom because they are different for different combinations. And we start with a graph tree coloring, it's a different circuit. If you start with a different puzzle, let's say a Sudoku puzzle that you want to prove, let's say you want to prove that you have a solution to a Sudoku puzzle without the other person knowing that you have a solution to that puzzle, then it's a different circuit. So how do you write that mathematical circuit, it's really hard to do it manually. And given that difficulty, there has been advancements in giving developers some tool where they can actually write that in some other higher level language that is more understandable. Those are these domain specific languages, for example, Noir, Circom, Leo, etc. So that is one way. The downside of this way is that a developer needs to learn this new language. This is not Rust or C++ or Java, right? They need to learn this new language. And the upside of it is that it's very optimized for a lean circuit, so that your proof generation can be less time memory consumed. Now, given its downside of not being so friendly to a developer, there has been invention with ZKVMs. What they do is that you don't have to learn a new language with them. You can start with, say, Rust. And this ZKVM can take that Rust represented computation and generate proofs for it. But they may end up with larger proof generation times or more memory requirements. And this is a trade-off. So there has been a huge amount of advancements as far as developer experience is concerned.
I see. So it seems like I hear a lot about ZKVM, but not so much about custom circuits. And it seems like you've kind of brought that back into the conversation. How would someone choose between the two?
Right. So we started off with custom circuits. That was the only way you could go from computation to what proof systems could understand. And then came along ZKVMs. ZKVMs have caught a lot of attention, has had a lot of mind share because of the immense improvement in there is some, they have lowered the barrier to entry so much, and justifiably they have gotten a lot of mind share. And so I started this debate on Twitter, and many people presented their opposing views, and my point there was that use something for what it is good at, right? You use ZKVMs because you want to embrace ZK easily. You use custom circuits to make things faster, right? And this is how the world has behaved in various sectors. You start with a generic solution, you embrace that for faster time to market, and then you customize things for to work with competition, where you want to be faster, you want to be cheaper, and for that you need to customize things. So I do think that there is a world where both can exist and both are important. There is no taking away from the power of both their contributions. And I do believe that for people, for developers who are trying to embrace ZK, I think ZKVMs are a very good starting point. And when they reach PMF, when they reach this huge level of adoption, when they are at a time in their product evolution where they have to think about scaling, that's when they need to start thinking about proof generation time, proof generation cost, etc. And that is when customizing their prover and verifier can become important.
I see. Okay. It seems like we've come a long way from me pointing at edges to what is possible with zero knowledge proofs today. Thanks so much for going through that evolution with me.
This was awesome. Thanks.